So I think we can start with the announcement. So it's a pleasure for me to introduce my colleague, Lutz Kämmerer, who belongs to the group of Daniel Potts at Technical University of Chemnitz. And he is going to talk about sample efficient sparse FFT for arbitrary frequency candidate sets in high dimensions. So please, Lutz, stage is yours.
Yeah, thank you, Tino, and thank you for the invitation, and welcome everybody to my talk. I will talk about this efficient sparse FFT things. What's it? As we saw in the talks this week, a lot of people assume that they know what is the important, or what are the important basis functions in order to approximate the functions, and then you can try to sample them best possible in some sense. And what we would like to do is to find out what are really the most important frequencies in some senses, or the most important basis functions. And clearly we do an FFT, so we are in a periodic setting, and we have monomials as basis functions. And that is the thing that is sparse FFT does, right? You just have a big candidate set, and you just try to determine whether which of the candidates, which of the basis functions are important, and try to compute the corresponding coefficients. And the next thing is that, yeah, we would like to do this in an efficient way, right? So this is the setting. So we have such a moderate trigonometric polynomial, right? So we have frequencies. These are these k's. So in a frequency index set I, and we have the corresponding Fourier coefficients. And the question is, yeah, how to get the Fourier coefficients? That's the usual question. But a much bigger challenge is how to find this index set. Yeah, right. So if you do not know what is this index set, and you just can sample this function, you would like to get out of this information, of the samples, what is the right index set. And okay, it is not, your candidate set is not the full space of integer vectors. So this is a d-dimensional vector, right? It's not the full space of integer vectors. You have some, yeah, potentially large candidate set where you know this I is in this gamma, but you do not know which of the k's that are in gamma belong really to I, right? So, for example, you have some assumption that you are an L1 ball, and in fact, the important frequencies, if you talk about function approximation, then the important frequencies, the important index set here is the blue one, for example, if you have such a bad assumption. But usually you have such an assumption. You have assumption that you have a hyperbolic cross, but you have only a rough assumption, right? You know that this is a hyperbolic cross, but you do not know the chord dependence on the different dimensions, and you do not know which dimensions are really coupling, and so on. And the question is now, can we find this blue index set without discretizing the full vector space of function space, yeah, finite dimensional function space, that belongs to this candidate. That's the point. And you can even do these sparse things, or these somehow scattered things, where you say, okay, frequencies are not almost closed, or something like that. So this index set can be an arbitrary thing. And the most important thing is that this dimension could be large, and not only two-dimensional. We talk about 10, 20, maybe 30-dimensional things. And the point is that if you estimate that your Fourier coefficients has a specific decay, and you have some slight overestimate of the weights or something like that, then you are exactly in such a situation. You have a hyperbolic cross, a huge hyperbolic cross, and in fact, the approximation of your function can be done with a few basis functions within this candidate. Okay, and the first thing and the simplest idea you can do is just to assume that this trigonometric polynomial is supported on I. Okay, gamma is a subset of I, And if this is relatively small, so then this number of terms in here is not as far away from the number of terms here, and then you can do you can treat this polynomial, right? And then you can use this polynomial. You assume that your frequency support is in this thing. You construct the corresponding sampling set such that the matrix has full common rank, and then you can compute the corresponding solution. Yeah, if this is, has full common rank, then you can use least squares, for example, and that leads to all the free coefficients, all these free coefficients, and clearly it leads to the non-zero ones, and then you sort out the zeros and you get this index. Okay, that's possible. And there are constructive approaches for sampling such a polynomial. Yeah, you can use random sampling or multiple rank 1 lattices. And the number of samples you need here is approximately this, this cardinality of this index set times the logarithm. And with this, you have a really constructive approaches, and you can do this in practice. But as it is shown here, this is a reasonable sampling strategy as long as this thing is not too large, right? So let's say 10 or 20 or maybe 30 times this index times the cardinality of this index set, then this is not the worst idea, I would say. And the computational efficiency, yeah, we talk about fast Fourier transforms. That means we are interested in fast transforms somehow. And okay, if you sample with random sampling, you get somehow unstructured metrics. In particular, if this index set is unstructured, or this index set is unstructured. And but you can do this in an efficient way if you use such a multiple rank 1 lattice discretization approach for such a polynomial. Okay. But what to do if this is not the case? So if you have gamma in the order of hundreds times the active frequencies, the number of active frequencies, I would say. Yeah. What to do? You just can determine all the non-zero Fourier coefficients, or you would like to do this, and you know that this number of non-zero Fourier coefficients is at most s. Right? And okay, you're interested in somehow sample complexity, which is sublinear. You're not interested in something that discretizes the whole space of gamma. And if this is a moderate relation, so let's say you have a factor of 100 or up to 1000 or something like that, the computational complexity can be linear in gamma. So if this is 1000, then this is and you have an overestimation of 1000, then you have 1 million candidates. Okay, you can do this, let's say. And you would like to have a computational complexity which is linear in gamma. But the point is that you do not like to consider the full matrix, right? So if you just apply some compressive sensing approaches, you know that you need S log S or S log gamma samples, and then you can consider the full matrix. But S log gamma times this this gamma or this cardinality here is a huge matrix, and you have at least for larger candidate sets or larger candidate sets and larger active sets, you have not really a chance to compute something. Okay, what's the idea? We would like to exploit the knowledge that our index set is somehow, or the cardinality of the index set is somehow nicely bounded, in order to construct the set of the sampling set, and then we would like to exploit the structure of the sampling sets for the computational complexity. Yeah, for getting a nice computational complexity, which is almost linear in gamma plus almost linear in S. Not almost linear in gamma times almost linear in S. It's a plus. That's important, and that's important for fast computations, right? And so, yeah, rank 1 lattices provide exactly the structure to do this. In what way? What is a rank 1 lattice first? So a rank 1 lattice is just an integer vector. You shoot your integer vector somehow in the space, and then you take an equidistant sampling along these integer vectors with m samples, right? And then so you have this long integer vector, and due to the periodicity of all these things, so we are in a periodic setting, we have trigonometric polynomials. We can shift this thing back in this unit cube. Okay, and what happens if you plug in this xj? You plug in this xj and you see, oh yeah, you put in this definition and you end up with something, with some coefficients. You have to sum up something, and you end up with this g hat L, and here you have a one-dimensional fast Fourier transform. You end up with a one-dimensional fast Fourier transform of length m. To compute this, you have a complexity of m log m, and to compute these g hat L's, and once you have this complexity, right? And now the question is the other way around, right? We would like to, or we say we know this p of xj, and we would like to have back the case and the p hat case in some sense. What can we do? Yeah, we can just apply, if we know all the sampling values in some senses, we just apply inverse fast Fourier transform, one-dimensional inverse fast Fourier transform, in order to get this g hat out. And that's it. And now, yeah, now we do not know what is the p at k and what's the k that belongs to the L. Yeah, and what we do is the following. We use this information, this g hat L. This is the formula. This is the formula from above. That means you possibly sum up some of the p hat k's that belong to your active frequency set. But we only know that they are in this gamma. And what we do is the following. We say, okay, if this g hat L is not 0, then all k's here in this frequency, or in this set here, all k's that belong to such a set here, may be non-zero. Yeah, one of them is at least 1, 0, but we do not know. So maybe all are non-zero. We do not know. And if this g hat L is 0, then probably all the p hat k's in the sum are 0. Yeah, and we do this in the following way. So this L is this k times z modulo m. So, and if this is non-zero, we say, okay, if this is non-zero, then this k1 belongs to such a set, to such a set where this g hat L is non-zero. Okay, then possibly this p hat k1 in gamma is non-zero. And you do the same for k2. Okay, if there is this g hat L, the corresponding g hat L is 0, then you say, okay, most probably this k2 is 0, and so on and so on. Okay, now you know somehow some estimate, and yeah, what you do is the following: you just use several of these things, and several of these things means that you shoot several directions in your space. In some senses, you take several integer vectors in order to construct rank 1 lattices, different rank 1 lattices, and for each rank 1 lattice you do the same. You compute this g hat L R. You take a look at those that are non-zero and mark it with a 1, all the k's that are in there, right? You can do this with the second one, and so on and so on, and you do this with L different things, right? And then you can say, okay, if my k1 is often in such a set where this g hat L is non-zero, then most probably this k1 belongs to a p hat k in this to active p hat k, right? And you do this for all these cases. So you just take a look at the number of lattices where they are non-zero, or where the things are non-zero, these g hat L's belonging to the corresponding case, and then you end up with an estimate at least which of the case belong to I and which not. Okay, that's the full idea, I would say, and and if you do this, you can show that if you have such a frequency set, so such a candidate set, you have an index set which is which has at most as elements an active frequency index set, and then you consider or then you can construct the sampling set which is based on random rank 1 lattices. We'll explain it in a minute. That has only s times the logarithm of gamma sampling values or sampling nodes, and then you use only those sampling values, the corresponding sample values, in order to identify this multivariate trigonometric polynomial P supported on line. You identify the frequency set, okay, and with a median argument, you can also compute the Fourier coefficients or estimate the Fourier coefficients. Okay, now this identification and the computation of the active Fourier coefficients can be realized, yeah, okay, this is in general this algorithm from above. This is this table and computing the scalar products. These are the Fourier transforms you do on the lattices. And this is the number of lattices you have in some senses. Okay, these are the arithmetic operations. And a suitable choice here is, for example, if n gamma is smaller or equal to 5s, but if s is let's say 1000 or something like this is not really a restriction, right? From minus 5000 to 5000. And you can fix m just as the smallest prime larger than this thing here, and the number of lattices you would like or you need to use in order to guarantee this probability here is the smallest odd number larger than this term. And really you see these are reasonable constants, right? So you have only constant of let's say 30 times the logarithm of gamma times s. Yeah, and you can choose the corresponding rank 1 lattice random. Yeah, okay, you just choose the generating vectors at random in this space, and then you have this nice probability. Okay, and now as I said, okay, if this relation here is really moderate, yeah, you can do this, because if this relation is not moderate, or let's say gamma is in 10 to the 20s or something like this, you have no chance to do this table, yeah, or to compute this table or save this table or something like this. But, and that's the point, there's a way out of this. So I called it here non-manageable gamma. So if this gamma is large, is really large, then you cannot manage this table thing, and you cannot manage the summation for each candidate, and so you have a problem. And so you need a computational complexity which is sublinear in this cardinality, right? And now the task is to determine the frequency set. So this set of frequencies, of active frequencies, out of a huge search domain from a low number of samples. Yeah, that's the idea. And there are several tasks, several various existing methods, and based on filters, Chinese remainder theory, Prony's method, and so on and so on. But there are different problems. For some problems, it's not clear, or it's even numeric tests show that non-sparsity is a problem, or there are no implementations because they may be not interesting because there are constants that badly depends on the dimension. Stability is clearly a problem. We do not know the theoretical things about our method, but lattices are usually stable. So there's hope that this can be a stable method somehow. And the point is, if you have many active frequencies, let's say 1,000, 2,000, or 10,000 frequencies, active frequencies, and you would like to compute all these things, yeah, you need some really fast methods. That's okay. Even fast in the cardinality of I, right? Not only fast with respect to this problem. Okay, and one way out of this is some dimension incremental approach. And the basic idea goes back to the 70s, and there are several papers that use several reconstruction methods for functions in some senses in these steps. I will show you the steps on the next slides. And you have this bounded orthonormal polynomial basis result. Yeah, which uses compressive sensing results. This works very well. They have, for the dimension incremental approach, they already have approximation estimates. Okay, we know, but we did this for the free basis and tried to make this more efficient to compute these things, or larger problem sizes, let's say. Okay, but only for the free basis in this talk at least. So, okay, what is the idea? The idea is the following: you have this high dimension high-dimensional thing. So let's say, okay, here it's only 3-dimensional, and even the candidate set is not so big, but let's assume that is our set. And now the question is how to find the blue ones if you do not know that. Yeah, these blue dots are the frequencies is this index set, and how to find them. And the idea is just to say, okay, maybe I can first find the first components of these blue dots, right? And what you do is you construct a sampling set, and the sampling set is a really simple sampling set. You just fix x2 and x3. You choose them randomly or something like that, and then you fix it. And okay, if you have fixed x2 and x3, then this is a function. This polynomial here is a function that depends only on the first variable. You do an equi-space sampling, and you use a one-dimensional fast Fourier transform in order to reconstruct. Yeah, you do not reconstruct the Fourier coefficients. You just reconstruct, projected Fourier coefficients. So sums of Fourier coefficients. And if you do this, and you see, okay, this sum of Fourier coefficients is non-zero, then at least one of the blue dots has as K1 this specific component, right? So you mark them here, just with the red. These are just the red dots. And okay, you have to repeat it because you possibly sum up some Fourier coefficients, and maybe you have some cancellation, so you do not see this the specific K1. But if you vary your x2 and x3, then the probability that this happens for all the different x2 and x3 is almost zero. Okay, or is very low. So, and now you have the first components, and you do the same for the second components. You fix x1 and x3, then you have a polynomial that depends only on the second variable. You just use the one-dimensional FFT in order to get these nice projected Fourier coefficients. You say, okay, here is the Fourier coefficient that is non-zero here, here, here. And okay, what is the next step? You know the first components of these vectors, you know the second components of these vectors. And now you know, yeah, the combinations of both are somehow a subset of these of the first two components of these elements here, right? And you do this by such a pairing, I would say, okay, or you just take the set product, and you're getting candidates. Yeah, and that's the point. You have a candidate set which is not huge. That's the moderate case from above. And compared to the number of frequencies you would like to have. Okay, and that's the idea. And the crucial idea is just to start with this set. Then you sample. Yeah, you need a nice sampling strategy, a reliable sampling strategy, which yields somehow the non-zero Fourier coefficients, which somehow sorts out the zero Fourier coefficients in some senses, or the small Fourier coefficients. And okay, you can do this. You have also a projection, so you fix x3 in this case here, and you compute projections. You compute several projections, and then you know which of the projections are non-zero and which are zero, or with high probability at least. And then you do this the next step. You go in the next dimension in K3. You fix x2 and x1. You apply this one-dimensional FFT in order to determine these projected Fourier coefficients. If they are non-zero, you say, okay, this case 3 is a candidate. Then you bring them together, yeah, all the combinations of these things, which is such a candidate set. This candidate set is moderate candidate set with respect to the number of elements compared to the target number of elements, let's say. You need some nice sampling strategy. You can do different things here, right? But it would be nice to have an efficient. And okay, you somehow identify the non-zero ones, and then you finish at the end with really the non-zero ones, or hopefully at least a subset of non-zero ones. Okay, and this step is somehow called pairing, or I would call it pairing, or equivalent. You can call this thing here pairing, and then sorting out in some senses. Okay, what do? You repeat each pairing step or times in order to avoid these errors caused by zero projections, right? So if you have Fourier coefficients that sum up to zero, you maybe lose something, so you repeat these things. There's a pseudo upper bound, that somehow depends on the success probability of the procedure, and this is linear in S, but this is really depending on the worst case analysis, and in practice this is much better than this. But however, there are upper bounds, and in each dimension incremental step, as I said to you, we obtain a reduced number of candidates. Yeah, you have not the full candidate set, not this full box. You have only a number of iterations times this S times this n gamma, which is the length of one dimension, one edge length in the dimension of this box. Okay, and these candidates, but that is the problem. These candidates form a possibly highly unstructured set. So maybe it's not really nicely structured, this thing. And so you require a fast transform, a sparse transform that can deal with unstructured sets. That's the point. Okay, and there are several methods from, you can use compressive sensing methods, you know, that then you get this nice sample complexity. But you have a computational complexity due to the fact that you will need to deal with the full matrix. And the full matrix is in the worst case at least, this times S times some logarithm in the size, right? So these are the elements. And there's another available method which I explained, or somehow sloppy explained you on the first slides, that you can discretize this candidate set. You know, this is the thing we used up to last year, I would say, this multiple rank walnuts discretization. That means we discretized this candidate set, and then we sorted out the non-zero ones, and that was our method up to that point. With let's say somehow bad sample complexity, at least if this n gamma is not so small compared to S. And a bad or a nice computational complexity compared to the compressive sensing approach, right? So you have only an S times n gamma, not an S squared times n gamma, because you do not need to consider the full matrices to apply some FFT method sensing. And now we exploit the information about the sparsity and bring together the structural benefits of the rank 1 lattices, right? So, and then could decrease the sample complexity to S log times this thing in each step, in each of these steps, right? And the computational complexity, which is in this thing here. So in these are the complexities of one step of this d-dimensional dimension incremental sparse Fft. And now we do this several times, and clearly you can plug in all these things and get an estimate on the number of samples you use during the whole process, right? You have this this candidate set, you have this I, and now this candidate set. That's the important thing. Your candidate set could be the full box, and it doesn't appear here, right? It doesn't appear here, it doesn't appear here. It's only the edge length of the box which appears here. So you're somehow can deal with completely unstructured sets, you can deal with structured sets. It doesn't matter. It holds for all nice sets you can imagine. Okay. And with this number of sampling values, you can use this dimension incremental approach in order to identify all trigonometric polynomials support I with a probability, with a high probability if this delta is small, and the corresponding identification. And that's the point, is it can be computed with a complexity which is rather small, I would say. So we have an d squared and s squared that is, let's say, a nice polynomial behavior for computations. With high probability you get this, in the worst case you get this, but in practice we didn't see this worst case. Okay. Here's some slide about total complexity of dimension incremental Sparse Fft algorithm, and here I need to say that this work here by Bozu and Mark and Felix, they used the cosine algorithm and they used compressive sensing results. Therefore, they have this gap in the sample complexity and computational complexity because they deal with full matrices somehow. But I have to be honest that they have really approximation estimates. Yeah, they know that their approximation that turns out of the algorithm or comes out of the algorithm is has a specific guarantee. That's the point. But you see that yeah, an S to the 5, even if they say okay, an S to the 4 in practice, an S to the 4 is maybe better, or is the thing you observe really. This S to the 4, even this S to the 4 is a problem if you have, let's say, S equals 1,000, 10,000, and you would like to apply this several times, right? And okay, with a multiple rank 1 Lutz discretization, we have a nicer sample complexity, a nicer computational complexity than this, and we even could decrease the sample complexity of this algorithm to this term. Yeah, right. You have not S squared times and gamma. You have just this thing, and this thing here comes from this R. As I said to you, this R is not so so bad as it is estimated in practice. Okay, that's the point. And now we can take a look at numerical examples, right? We have an implementation in MATLAB. We have, or usually we fix this parameter R, these iterations, by 1 or 5 in practice. 1 is not really good in practice. Let's say in practice, if you consider artificial examples, let's say. But 5 is in practice seems to be enough. Why? Because you do this in order to avoid cancellations, right? And these cancellations are really not very often, or it's really not the problem that there are many cancellations or something like that. Yeah, and clearly I showed you that this thing works for polynomials with high probability. But now you can also apply the whole algorithm in order to approximate yeah, suitably smooth functions in some senses. And in order to not only approximate suitable smooth functions, you just try to find the most important frequencies. That means the most important basis functions, the most important monomials of this multivariate function, right? And we tested this thing up in dimension up to 30, and with sparsities up to 100,000. Yeah, that's the point. And the first numerical example here is an artificial one. I would say you have a polynomial, really in polynomial, you have a huge candidate set, right? A huge candidate set, and we just draw the Fourier coefficient, or at first we draw the frequencies. Yeah, the active frequency is uniformly at random, and then we draw the corresponding Fourier coefficients at random. And since you draw these things at random, you have no cancellations in this projections. In fact, or in practice at least. And so we use this parameter R equals 1. And as you see, as I said, this behavior of the total number of samples compared to the sparsity is really almost linear, I would say. So it's a double logarithmic plot. It's not sure that it's linear, but it's almost linear at least. And what you see is that, yeah, the random rank 1 lattices, though the new approach compared to the discretization approach in each step, leads to reduced number of samples, which is a factor of approximately 10, I would say. And you see this, and in addition, you see a linear factor in D somehow. Yeah, you have here a factor of, let's say, 10 times more samples you need in dimension 30 compared to dimension 5. Okay, this is somehow an artificial example. This is also not yeah, somewhat constructed example, but it's an approximation of the function. We have a B-spline and yeah, tensor product B-spline in some senses in dimension 1, 3, and 8 of order 2. So this is the yeah, the most or the has the low smoothness, and then you have a 4-dimensional B-spline of order 4 in dimension 3, 5, 6, and 10, and so on, and the 6-dimensional in 6 order in dimension 4, 7, and 9. And okay, we just assume nothing. Yeah, we just assume that our frequency set is in this set somehow, and we just try to approximate this function by the polynomial that comes out of our algorithm. That's the idea. And what should come out? Yeah, it should come out some hyperbolic cross, some 3-dimensional hyperbolic cross, depending on the 1st, 3rd, and 8th dimension. Some 4-dimensional hyperbolic cross, which is possibly smaller due to the higher order of smoothness here, and here the same 3-dimensional hyperbolic cross, and the union of all of these things should be the frequency index set which comes out of this process. And indeed, it's the thing that comes out of this process. And okay, you see here the L2 arrows. Yeah, we just said, okay, this is our search space for the candidates, and then we search for the 1,000 up to 10,000. Yeah, in some senses best possible, or yeah, best possible monomials. And unfortunately, I did not plot the truncation error, but this is really the best possible or the error of the best benchmark approximation. But I think this is very close to this. We took a look at it, and pretty sure that the best possible you can do is really close to this. Okay, at least in monomial basis. Yeah, well, what do we have here? We have the total samples. Yeah, we have this L2 error compared to the total samples, and you see even for function approximation, this new approach, so the random rank one-lets approach, does not suffer from larger number of samples or something. We have also this approximately this gap, the same gap here, right? That we save a number or a factor of 10 for the samples, or approximately 10 for the samples, or maybe 8 or 7 or 6 or something like that. And that's very very important if you have some process that that has a certain or which is not too cheap when you sample, right? Then this is a nice thing to save a lot of samples. Okay, so that's the summary. Yeah, you see that the sample efficient identification of multi-rate trigonometric polynomials can be done based on random rank one-letters, and if you have a moderate size of your candidate set, you can do this just straightforward, and you do not need some additional things. But if your candidate set is really huge, you can use a dimensional incremental approach in order to split them up in a moderate number of reading step sizes. Yeah, and there's still several open problems. Okay, there's
please switch off your microphones, please.
There's a question on stability, clearly, and it's not clear, or it's not really clear how good are the approximation properties of this process, of this algorithm. But I'm pretty sure that we can estimate some approximation results, but we haven't done it yet. And yeah, and the question is whether or not our model of estimating this R is the right one, which leads to this large number of R in theory, but in practice we do not see this. So perhaps we should use another model and estimate this thing in much more closer way to the practice. Okay, so thank you for your attention.
Thank you very much, Lutz, for this very interesting talk. Are there comments or questions? Okay, maybe I start. So Lutz, there is this paper by Stefan Kunis and Holger Rauhut, right?
Yep.
there are two parts, and I'm not sure in which part they deal with the multivariate case, but they also recover like trigonometric polynomials with sparse frequency set with compressed sensing, like in the classical sense.
Yeah.
And if I understood that correctly, they get like sampling bounds of typical compressed sensing fashion, like sparsity times logarithm of, let's say, the set gamma, which is gamma in your notation.
Yeah, yeah.
So how does that compare? I mean, I know that usually it's this universal thing in compressed sensing that you have several index sets which work with one like random draw, but in your case, it's a kind of adaptive thing, right? You do a different thing for different index sets, isn't it?
No. It's really so that you choose your things. So we have to differ. But this first approach for the moderate, and that's the problem, right? So if you have this moderate relation, yeah, such that you can take a look at each of the candidates, then this is not really adaptive, because you just fix your M, you fix your L, and you choose your vectors at random, and then they provide such a nice sampling strategy.
This is the usual compressed sensing.
Yeah, that's right. But the difference is that this is more efficient, right? This is more efficient to compute. That's the point. And if you have if you go in this dimension incremental approach, yeah, you need also, for compressive sensing, you need also this dimension incremental approach if this gamma is too big, right?
Yes.
If this gamma is too big, you cannot do anything. And if you go in this dimension incremental approach with this method, you save a lot of time. That's the point.
But here you still have the cardinality of gamma involved, right?
Here you have the cardinality of gamma, but in this dimension incremental approach, your candidate set is not the full gamma. It is this pairing thing, right?
Okay, I got it. Yeah.
That's the point here, right? So it's more or less such a set or such a set. So you split up with the dimension incremental approach. You split up your big set to several small sets, which you can treat. That's the point. Yeah.
Okay. So you managed both. You managed a good sampling complexity, and you managed an efficient computation.
Yeah, right.
That is really interesting. That one theorem I found interesting. It was maybe in the last third of the talk, where this. Yeah, that one. That one. Yeah. That looks really nice. So
yeah. You can do another strategy where you can improve this depends on S even more, but that is the point Mark will talk about, I think.
Okay, so here's the connection to Mark's talk in the afternoon.
Yeah, at least in one direction. But then you do not have this, or you have some problems if you do this general assumption. So you need somehow a nice candidate set, and for this candidate set you need reconstructing like one lattice first. And if you have this, then you can do several things on this line and so on.
Yeah, this is really interesting. So thank you very much. Are there further questions? I see Mario on the list. Mario, do you have a question?
Not this time, but thanks for the question.
Yeah, good. So Lutz, if you agree, your recorded talk will be kind of made accessible. Okay. And maybe you can send the slides also to one of us.
Yeah.
And then we can also make this accessible. Okay, so thanks you two for doing the morning session.
Yeah, thank you.
Yeah, so we will restart again in the afternoon at 3 o'clock Moscow time with the 2 lectures by Albert Cohen. And afterwards, Mark Ivan.